Hi everyone, today I'm going to talk about the solutions for Atcoder Beginner Contest 383 problems A to F. And for the first problem, we have one humidifier that currently has no water, and we need to add water to this humidifier n times, and for each time we're given the time and the amount of water that we add. And however, this humidifier has a leak, and each unit of time, the amount of water decreases by 1. And we need to find the amount of water that is remaining in the humidifier after we add water n times. And for this problem, since n is small, we can just directly simulate the process. And let's look at the code for more details. So we first just input all the values as pairs, and since the time are given in increasing order, we can just loop through the array without sorting it. And for each time we add water, we compute the delta time between the next time we add water and the current time. And this means that during this interval, the water level in the humidifier will decrease by this amount of time. Since each unit of time, the water decreases by 1. And we can just keep track of a count, which is the amount of water in the humidifier. Initially, there is no water in the humidifier, so we just set the count to 0. And afterwards, each time we add the amount of water into count, and we subtract the count by the minimum amount of water that's currently in the humidifier and the time in between the current time we add water and the next time. And for the last operation, we just need to add the amount of water that is added at Tn. And afterwards, we can just print out the count. Next, for problem B, we still have humidifiers, but this time it's 2 humidifiers are in a grid of H rows and W columns, and we are given the state of each cell as a desk or a floor, and we can only place humidifiers on floors, and we need to place 2 humidifiers and find the maximum number of cells that can be humidified. And this part says that a cell can be humidified if the distance between the cell and one of the humidifier cells is less than d. And we notice that there's only 10 rows and 10 columns. So this is extremely small, and we can just simulate all the processes and try putting humidifiers in all the possible cells. And let's look at the code for more details. So we first just input all the values for the grid, and afterwards we loop through x1, y1 is the first location for the first humidifier, and we need to check if x1, y1 is a desk or a floor. And so we need to make sure that x1, y1 is a 4. And afterwards, for this part is just looping for x2, y2, which is the location for the second humidifier. And for this, we need to make sure to check if the second humidifier is at the same location as the first one, or if it is not a floor, then we need to continue because we need to make sure that the two humidifiers are at separate locations. And the next part is just counting the amount of grids that are humidified by these two humidifiers. So for this part, we just need to check if their location is within a distance d of one of the humidifiers, and if so, we just increment the count. And we keep track of an answer. And for answer, we need to initialize it to 2 since the places where we put the humidifiers are considered humidified. And for this part, we can just compute the maximum for the answer. And yeah, afterwards we just print out the answer. Next, let's look at problem C. For problem C, it's still the same problem, but now where there is multiple humidifiers placed on the grid. And again, cells still represent if they're walls or if they're a floor. And in the case of an H, that means that the cell has a humidifier placed. And we need to count the number of humidified cells, which are the cells that can be reached by a humidifier from at most D moves up, down, left, or right. So for this problem, we can use a multi-source BFS and start from all the cells that currently have humidifiers. And we can look at the code for more detail. So for this problem, we first input all the values, and for locations that are marked with H, we can push them into a queue so we can perform BFS afterwards. And we need to push the location, which is I, J, and the distance that the point has already traveled, and currently it is 0 because it is still on the location with it, H. And for this part, we're performing BFS on all the cells that have H. And initially, we just pop out the location and we can mark it as H. And afterwards, if the distance is already at the maximum, which is D, or if it's greater than D, we can continue. And this part, we're just looping through all the possible locations where a cell can travel afterwards, which is up, down, left, and right. And for the new location, we need to check if it is still within the boundaries of the cell, and if it is equal to a dot. And this ensures that the cell hasn't been traveled to before, since we need to make sure that we only loop through each cell only once, because that will ensure that the time complexity is still H times W. So we can't loop through the grid multiple times. And since we change the grid, once we visit it, we change it to H, then by checking if the grid is still a dot, then this ensures that the cell hasn't been visited multiple times. And if this is the case, we can push this cell into the queue. And afterwards, when all these cells have been updated, then we can just loop through the entire grid and check if the current cell is equal to H. And if it is, then it means that it has been reached by a humidifier. And we can increment the answer. Next, let's look at problem D. And for problem D, we're supposed to find the number of positive integers not greater than n that have exactly 9 positive divisors. And this problem can be solved with number theory. And let's look at it further. We can calculate the number of divisors by first factoring the number. So if we have a number that can be written in this format, then the number of divisors would be k1 plus 1 times k2 plus 1 all the way to kn plus 1. So this is because for each number, it can be, let's say for P1, it can be 0 or 1 or 2 up till k1. So there's k1 plus 1 choices for this prime number. And for each of the primes till Pn, this is all the case, and we can just multiply all the possible combinations together to find the number of divisors. And so in this case, we're looking for numbers with 9 divisors. And so n can be 1 prime to the power of 8, since this will have 8 plus 1 divisors. And for the other case, since 9 can be factored as 1 times 9 or 3 times 3, then this means that n can also be 2 primes multiplied together, and which can be p1 to the power of 2 and times p2 to the power of 2. And this is also 2 plus 1 times 2 plus 1. So also 9 divisors. And so we can just find a list of primes and count all of the possible combinations of that can make these numbers. So since n is 4 times 10 to the power of 12, however, we notice that n is always p1 times p2 squared, so we can just find the primes that are in square root of n. So that is 2 times 10 to the power of 6, and so that is in the time range. So let's look at the code. So since we only need to compute primes up till the square root of n, I first find m, which is the square root of n, and I divide m by 2 because the smallest prime is 2, so that means that I can just find primes up till m divided by 2. And afterwards, this part is just creating the list of prime numbers. So P will be the list of primes, and each time I just loop through numbers from 2 to m. And I have a Boolean array called prime, which will just store if the number is prime or not. And so if the number is still prime, then I will push it back into the P vector. And afterwards, I will update all the values that are multiplied by the current number and change them to false. And so after I have my list of primes, I can just loop through them, and this part, K, is just finding the maximum value for the other prime, since the current prime is pi, and we need to find the maximum value for pi multiplied by another prime number that is still less than n. So j is the upper bound, and this means that all numbers after j will not work, since when it is multiplied by pi, it will already be greater than n. And so this means that all the numbers in the range of the current number till j will all be possible, and we can just add the number by j minus I minus 1, because we need to minus 1 because we can't have pi multiplied by pi. And if not, this means that pi is already too large for any other prime to be matched with it. And so we can break out of the loop. And so in the current loop, we're just checking for the case where there are only two primes. Like the case where p1 square root of to the power of 2 multiplied by p2 to the power of 2. And so in the end, we still need to add the case when it's just a single prime to the power of 8. And so initially we can compute the maximum for this prime by finding the square root of square root of square root of n. And for this part, we're again just finding the upper bound for this prime. And so anything greater than j will not work, and anything smaller than j is still a valid prime. So we can just add j to answer, and this means that we're computing the part for a single prime to the power of 8. And for problem E, we have a graph with n vertices and m edges, and the weight of a path between x, y is defined as the minimum possible path weight of a path from vertex x to vertex y. And a path weight is just the maximum weight of an edge in the path. So now we're given two sequences, A and B, and we can permute B so that summation f ai bi is minimized. And let's look at the algorithm for this problem. For this problem, let's first look at how to compute the answer for only fxy. And so we notice that fxy is the minimum possible path weight, so we can just sort all the edges in increasing weight, and then we can loop through the edges and add the edges into, like, we can use a DSU and unite the two vertices of the edges as we loop through all the edges in increasing order. And a path connects two vertices, so if x, y are united together in the same component, then that means that the edge is the minimum pathway that can unite vertex x to vertex y. And so as we loop through all the edges with increasing weight, the first edge that joins x and y into the same component will just be fxy. And however, after we know how to compute fxy, this time the problem is asking us to loop through permute b so that fab, the summation of faibi, is minimized. So we can just still use the same concept but greedily add all the vertices into our answer. So we need to keep track of the number of A vertices and B vertices that are in each component. So we can do that in a count A and a count B. And we still loop through all the edges in increasing order of weight. And for each group, when we unite the vertices in the connected by the edge together, we can add the minimum number of A vertices and B vertices in the component into our answer. So that means we can pair up, since there are some number of A vertices and some number of B vertices, then if we find the minimum, that means we can know the amount that we can pair up. So since we can permute B, we can add all the available vertices that we currently have. So let's look at the code for more details. And so we just sort all the edges in increasing order of weight. And CA is to keep track of the current number of A vertices that are still unpaired in the current component. So this part is just the disjoint set, and this part we add in all the counts for the current component. So initially all the vertices are in their own component. So CA of the current vertex is just 1 because there is one vertex which is AI and it is a vertex of A. And this part is doing the same thing but just adding the number of vertices in B. And this part we loop through all the edges in increasing order of weight and unite the components if they're not in the same component already. And so A1 is just the original number of vertices in A in the first component, and so on. And we can unite U and V. And after we do so, all the vertices A vertices that are initially in the two components separately are going to be added into this component. And the same thing occurs for the B vertices. And this means that we have CA vertices available and CB vertices available, which both have f x, y equal to the current edge weight. So this means that we can pair up the minimum of these two counts, the count A and count B, and we can pair up these vertices which have f x, y equal to the current weight. So we can just add count times W into the current answer because we can pair up count number of pairs. And this means that of the number of A vertices available, we already used up count. And so we need to subtract count from CA and also subtract count from CB. And after we loop through all these edges, we can just output the answer. And for problem F, we have n products for sale in a store, and each product has three attributes which are price, utility value, and color. And we need to choose some of the products to buy. And we only have X dollars, so the total price needs to be less than or equal to X. And our satisfaction is calculated as the sum of utilities plus the number of distinct colors times K. And we need to choose out of these n products so that our satisfaction is maximized. And we can solve this problem with dynamic programming. Since we need to know if the item is the first one that is chosen of that color, we can create dp as dpij, which is similar to all other knapsack dps where I is the first I items and j is the price. And so dpijk will just be the maximum satisfaction of the first I items when price is less than or equal to j. And we can, because in this case we also need to know if the item is the first one that is chosen, like the first one of that color that is chosen. So we need to keep track of a third dimension which is 0 when only one item of the current color is chosen, and it is 1 when the current color item has been chosen multiple times, and it is 2 when no items of that color has been chosen. And to easily compute this, we can group all the items with the same color together, so we can sort the items by increasing order of colors, and we can look at how the DP transitions further in the code. And so we create our DP array with I, the price, and then K, which is 0, 1, and 2. And we first sort all the items with increasing order of color so that all the items with the same color will be grouped together. And as for the DP transition, we need to check for two conditions. So pre is just a variable that records the last index of the previous color. So this records when the color transitions to another color. So the first case, we're checking if I-1 is equal to pre, and this is just checking if the ith item is the first one of the current color. So if I-1 has a different color than then this means that I is the first item of the current color. So if this is the first item, dpij2 would be the maximum of dpi-1 j0 and I-1 j1 and I-1 j2. And this is because the previous item is of a different color, so we can choose however number of items we want, since dpij2 is the case when none of the items of the current color are chosen, so it has nothing to do with however many items we choose for the previous color. So we can just find the maximum satisfaction out of all of those possibilities. And for dpij0, this means that there is only one item chosen, and since it is the first item, we can also find A, which is all the possible number of items chosen for price j minus items I dot p. So because the current price is j, we need to transition. If we want to add this item, we need to transition from all the previous DPs that have price j minus items I dot p. And since again this is another items of other colors, so we can also choose however many items we want. So it can transition from k equal to 0, 1, or 2. And dp, and this is when j is greater than or equal to the current price of the current item. So if it is not, then this means that it is impossible to choose the current item. But however, this DP states represent when only one item is chosen. So if it is impossible to choose, then we can set the DP to negative INF, because this means that this case is impossible. And since dpij1 represents when more than one item is chosen, and since we're only on the first item of this color, then it is impossible to have this case, so we can also set it to negative INF. And for the second case, these are when the ith item is not the first one we've checked for the for this color. And so dpij2 represents when none of the items of the current color are chosen, and this is just equal to dpi-1 j2, since I-1 has the same color as I. And And this is the case when there are no items chosen when the first I-1 items are computed. And for dpij1, then this means that there are already more than one item chosen. So this can be transitioned from I-1ji, since if the current item isn't chosen, then there must be already more than one item chosen in the previous I-1. And otherwise, if we want to choose this item, then it can come from the previous state when there is only one item chosen, which is this part, or if there are already multiple items chosen in the previous state. And otherwise, if j is greater than or equal to the current price of the item, then it is possible to choose this item. Otherwise, it is not, and the only case will just be if the first I-1 already has multiple items chosen. And the DP will transition similarly for the case 1 for dpij0. We can also choose to choose the current item or not choose the current item. If we don't choose the current item, then it will just transition from I-1j0, since it is the state when only one item is chosen. And if we choose an item, then we have to transition from I-1j minus the current price 2, since 2 represents when none of the items are chosen, and ij0 is the state when the first only one item is chosen. So we must transition from the state when none of the items are chosen. And since this is the first item, then our number of distinct colors will increase by 1, and so we need to add k to our satisfaction value. And at the end, we just find the maximum out of all the possible results.